Lesson 60 has two parts. The first part is on more about polygons and angles. And so here in part A, we're going to apply some of the new rules and definitions. Make sure you've taken a look at those, and just a few new rules on polygons, and then some definitions on polygon types and diagonals. And we'll also be connecting these new rules and definitions to old ones from lesson 44 and 53. So you might want to take a look at those too. And we'll be solving some new problems about polygons. So let's just go ahead and jump right into that. And example 60.1 here, solve for side x. Now, one thing you'll notice in geometry that if you remember the rules, the problems can often be really easy to solve, but then they're impossible if you don't remember the rules. So take some time each day to memorize rules and definitions, including old ones from lessons 44 and 53. So you might remember from lesson 44 that you learned that sides opposite equal angles have equal measures. And notice the two angles at the bottom of the triangle. They have one tick mark each. So that's used in geometry to represent congruency, equality there. And so that's telling you that those two angles are congruent. So since the two angles are equal, the sides opposite are equal. So the side opposite this angle is the same as the side opposite that angle, since the angles are equal as well. So therefore, x equals 9 centimeters. It's the same length as the other side. Moving on to problem 2. Given a convex pentagon, find A, the sum of the interior angles, B, for a regular pentagon, the measure of each interior angle, and then C, the sum of the exterior angles. So we'll be applying some of our new rules and definitions here, but starting with A, the sum of the interior angles. And from lesson 53, you learned a pentagon. That means pent means five sides. So a convex pentagon, it doesn't have to be all the sides perfect. That's what a regular pentagon is. A regular pentagon is convex, but it also has all the sides are the same length. So all you need to do then is use the new lesson 60 rule and evaluate n minus 2 times 180 for n equals 5. And so we'll just say 5 minus 2 times 180. We just substitute in there for n, which means the number of sides, and try not to make things too complicated. That's a descriptive variable there, n for number of sides. So 3 times 180. You can use your calculator if you want. It doesn't say to, but hopefully that's a pretty easy problem for you to do in your head, or just do on paper real quick. 3 times 18 is 54. Add a 0, 540 degrees. B, for a regular pentagon, find the measure of each interior angle. Think about a regular pentagon. It might, I'm not going to make a perfect one here, but it would have a shape like this where all the sides are the same length. And so angles opposite all of those sides of the same length, those are congruent as well. So we could actually put one tick mark on each one, because we're saying that they all have the same measure when we do one tick mark on each one. So if we know the sum of the interior angles is 540, which we figured out in A, just divide that by 5. And so 5 goes into 540. 5 goes into 5 one time, and then we bring down a 0. It goes into that 0 times, bring down the 0 in 40, and so 5 goes into 40 8 times, 108 degrees. That's how much each of them equals. 108 degrees for each of them. And it looks like that too, right? 90 degrees is a right angle, 108 is obtuse. They look a little bit obtuse on that pentagon. C, the sum of the exterior angles. So again, just to understand this, let's just draw as good as you can it's good to draw things even if they're not perfect for this. So we have a pentagon there. We're trying to draw a regular one. It doesn't have to be a regular because this works for convex pentagons. It doesn't have to be a regular one, but the sum of the exterior angles, what is that? Now, think about this. If this was a regular pentagon, just pretend like it is. If that angle is 108 degrees, do you see the supplementary angle there? And how this one here is supplementary to 108. So that means they would add up to 180 degrees, right? So this one here must be 72 degrees. And so then you're going to have another one of those right here, and we'll just do a single tick mark, but we'll do it in a different color. So we're saying that that one is the same as the other 72 degree, and so then there's going to be another exterior angle right there. And let's just keep going around clockwise here around this. Another 72 degree angle there, and then last we'll have another one here, assuming this is a regular pentagon again. And then 72 times 5, that's 360 degrees. And that is one of your rules, right? The sum of the exterior angles of any convex polygon is 360 degrees. It doesn't have to be a regular pentagon or an irregular pentagon. It can be a convex decagon, an octagon, a quadrilateral or rectangle. The sum of the exterior angles is 360. So we actually didn't have to do all of that and do the math right here. I was just doing that to show you that it works. And it works for this pentagon example here, but it would work for any convex polygon. So interesting little rule there that if you know it, it's just all you got to do is just go 360 degrees and you're done. If you forget the rule though, then that'll make that a whole lot more complicated. Let's do one more. Example 3, given the concave hexagon shown, use diagonals to break it into triangles. Then find the sum of the interior angles, remembering that the sum of the triangles, interior angles, that equals 180 degrees. You learned that in lesson 44. So that formula for interior angles, n minus 2 times 180 degrees, that also works for concave polygons, because we can break a concave polygon into triangles, which are always a convex polygon. You can't draw a triangle and have a concave side like that we have on this hexagon here. And so that's what we're going to show here, is just kind of how that works for concave polygons as well. So since the sum of a triangle's interior angles equals 180 degrees, you just count the number of triangles formed when you put these diagonals in and multiply by 180. So let's add some diagonals. Let's just start right here. There's different ways we could start, but if you do it the right way, it's all going to end up the same way, drawing diagonals like that from one vertex to another. And so we have 1, 2, 3, 4 triangles there. And so we know the sum of each of those is 180, so if you just do 4 times 180, that's 2 times 360, that's 720 degrees. Okay, that's the same thing we would get if we did n minus 2 times 180, right? Because 6 sides on that concave hexagon, 6 minus 2 is 4 times 180, 720 degrees. So that formula works, whether it's concave or convex. Moving on to part B, and transformations, and a change of position, size, or shape of a figure. That's called a transformation. So here in lesson 60B, we're only going to consider transformations of position. Okay, so the new figure will always be congruent, equal shape, right? That's what congruent means. It'll always be congruent to the original figure. So transformations there of particular importance to someone like a computer-based designer or a graphic artist who's constantly transforming shapes as part of their work. And we'll consider 3 types of transformations of position here. One of those is a translation or slide, which is just a shifting of every point on a figure an equal distance. So this point B, it goes over here, we call it B prime. That's a lot of times that's what you'll see in a translation is B goes to B prime, A goes to A prime, but it's going to move the same distance over. C goes to C prime, D goes to D prime. They all move the same distance over. And we're going to do this on a Cartesian coordinate system, so we'll discuss the coordinates of the new position when we do example problems. Another type of transformation is a reflection or flip, which creates a mirror image of a shape across a line of reflection. So the shape below, that's reflected around side CD. And sometimes a shape might be reflected around the x-axis, around the y-axis. It may be reflected in different ways. It looks like a mirror image. Notice how point C there and C prime, they basically touch each other. Point D and D prime, they basically touch each other. They didn't really move in this example. Some reflections they do, but it's not like a transformation where everything moves the same distance. And the third type we'll look at is a rotation or turn, which rotates or pivots an object relative to a fixed position on or near the original object. So here we're doing this relative to point D, to vertex D there, and rotating it in this clockwise direction. But it could also be rotated about an origin or some other location as well. And just comparing that to a translation and a reflection, you can tell it's not just slid. The new polygon is not just slid to a different location where everything moves the same distance. And it's obviously not a mirror image either of the original polygon there. Let's do a couple of examples here. Example 4, translate rectangle ABCD to the right 5 and up 2. What are the coordinates for the new vertices of A prime, B prime, C prime, D prime? So we see that rectangle ABCD, and we want to move it to the right 5 and up 2. So that means everything moves the same distance. So the best way to make an accurate translation is to first identify the coordinates of vertex A, then add +5 +2, because we're moving right. That's a +5 to the right, and then up would be a +2. Add that to vertex A and mark that on the graph. And then we can redraw the same rectangle. As long as we have a starting point, we can redraw the same rectangle and then identify those coordinates A prime, B prime, C prime, and D prime. So, I mean, you can tell this rectangle is a 3 by 1, 2, right? So if we move A to A prime, then we should be able to redraw the rest of the triangle, right? And we've been asked to find the coordinates for the new vertices. So keep that in mind too. What's the focus here? What are we trying to find? So A, find point A first. To the left, 1, 2, 3, 4, 5, 6, 7. It's at -7. And then down 1, 2. So it's at -7, comma, -2. Okay? To that, we want to add, to the -7, we want to add 5, and to the -2, we want to add 2, because we're going up 2. Okay? So let's just do the math over here on that ordered pair, those coordinates there. So -7 plus 5 to the right 5, comma, -2 up 2, so +2. So that ordered pair then becomes -7 plus 5. That would be a -2, comma, 0. Okay? So that is where A prime is. And we'll use a different color to represent A prime. So A prime is right here, right? That's to the left 2, up or down none. So let's write that, A prime. And then from there, we could go to the right 1, 2, 3, right here. There's B prime. We can go down 2, there's C prime, and then go back to the left 3 to put D prime. And so then we can just connect those dots to make our rectangle A prime, B prime, C prime, D prime. And so there it is. So we've been asked to find those coordinates. So now we're able to do that. Let's just write them over here. A prime is, like we said already, minus 2 comma 0. B prime, that's equal to 1 comma 0. And then C prime, that's to the right 1 and down 2. And then D prime, it's a rectangle, so I mean, you can see how it's vertical there, so I mean, it makes sense that that would have the same x coordinate, right? Minus 2 and then down to minus 2. Okay, so there's the new coordinates, and that's the translation as well. Now, you didn't have to draw the translation when you do these on the practice sets and other places, but that is a good way to get started, right? So you figure out what one point is, and then from there you can figure out the rest of the points just by redrawing that rectangle. Let's do one more, and we have a transformation there. We see the prime transformation shape there. It's a pentagon, and we're asked, is that a translation, a rotation about the origin, or a reflection about the x-axis? What's going on here? So, I mean, if you imagine a mirror along the x-axis, you can probably already tell this is going to be a reflection about the x-axis, right? This axis is called the x-axis. This one is the y-axis. So it's pretty obvious there that that is a reflection about the x-axis. So it's not a translation because there's no way to slide that in a way that would make it upside down. If it was a translation, it would still be A, vertex A would be at the top, right? But it's not. It's not a rotation because, well, you really have to use your imagination to understand that, but it's good to try to consider this. And it asks, is this a rotation about the origin? So to rotate it relative to the origin, consider just this edge right here, edge DC, okay, from here to here. Consider that only, okay? You'd have to rotate that through 270 degrees to get it to quadrant 4. Okay, so it's here right now, and if you want to rotate that 90 degrees, then that would be going this way, right? And so here would be D, here would be C, and we'll just write underneath this, that'd be 90 degrees. Now, rotate that another 90 degrees over to 180, and it would look like this, right? And just to kind of try to draw this the way it would be, that D would be upside down, then C would be there. That's 180 degrees. Now, 90 degrees, I mean, think about this. Drawing just a little line from the origin there to try to rotate that 90 degrees. Think about a 90-degree angle there. It'd be right there, right? It'd be right around in there. And then 180 degrees, it'd be over there. So hopefully it makes sense. 270 degrees going all the way to there, that's going to get it into quadrant 4. But at 270 degrees, it's going to be like this, right? So side DC would actually be here. That's rotating at 270 degrees. Is that what side DC is doing in that example? No, it's right here. Okay, it's not straight up and down vertical. So that shows you right there that it's not a rotation. It's a reflection. So again, if it looks like a mirror image, then it is. Okay, well that's all for lesson 60.